Welcome back. We're going to begin discussion on a new topic, and that would be substitution and elimination reactions of alkyl halides. Now, there's parts of it that you don't know, so I think it's better. Let me walk you through the objectives of this lesson. And this is a large topic, so what I have done here is tried my best to keep it to a minimal level of complexity. Okay, so I've tried really hard to keep it as less complex as possible. So with that said, let's look at the objective. So after completion of this particular unit on substitution and elimination reactions, you will have a comprehensive and conceptual understanding of what constitutes a nucleophile. Now, if you remember your Chem 170 or 175 coursework, you have come across the idea of a Lewis acid and a Lewis base. A Lewis base is something that is rich in electrons and is willing to donate those electrons. A Lewis acid is one that's deficient in electrons and is more than happy to receive electrons. So for our current topic of discussion, we are only going to use the term nucleophile. We will come back to the term electrophile as we move further in the coursework. All right. Now, as we look at both substitution and elimination reaction, there is something that's very, very important, and that is the reaction substrate. Now, you may have a reactant. A reactant consists of one component of a reactant is your substrate, and one component of it is your leaving group. Okay. So reaction substrate, the reaction substrate itself controls whether a reaction would be a particular type of substitution or particular type of elimination reactions. Okay, so the nature of the substrate is just as important as the second thing, the leaving group, right? So there's two components to every reactant that we will see. Okay, one of the component is the substrate itself, to which is the leaving group is attached. Okay, and the leaving group also affects the reactivity of the reaction, right? Now, we will primarily look at two types of substitution reaction. One of them is SN2, and the other is SN1. Okay, elimination reactions. For time being, we're only going to consider E2 and E1, and I'm going to make a separate video when we finish with the first 4 reactions on E1CB. Now, E1CB is elimination 1 conjugate base. Now, that's a special case of elimination reaction, but I want to get us through SN2, SN1, E2, and E1 first before we even focus on E1CB. Okay, and now you're not entirely unfamiliar with the idea of inversion and retention of configuration. What did we learn in Chem 330? Let's say you start with an R. If you end with an S, then you have inversion of configuration. If you start with an R, you end with an S, then you have if you start with an R, you end with an R, then you have retention of configuration. If you start with, say, an R and you end with half of R, half of S, then that's called a racemic mixture. Okay? All right. Before we get too far into this topic and get wound up with SN2, SN1, E1, E2, etc., let's understand what is a nucleophile. Okay, as I mentioned earlier in the objective, as we were discussing the objective, a nucleophile is nothing but an ion or a compound. It could be an ion, which means it has to be positive or negatively charged. And if it's a compound, means it could be neutral. So a nucleophile is an ion or compound that is rich in electrons. Okay, for something to be a nucleophile, it must be electron rich. Okay. Now, typically nucleophiles are negatively charged, but can also be neutral. Okay. Now, you do not have to remember this list of nucleophiles. Okay. What I have done here is highlighted the 2 neutral ones, because the remainder of the nucleophiles are negative. So I just wanted to take the time to just point out why water and ammonia are good neutral nucleophiles. As you can see, water, the oxygen contains two lone pair of electrons, okay? That makes oxygen electron rich, which means it makes water a neutral nucleophile, means again, it's rich in electrons. So is ammonia, okay? Nitrogen contains a lone pair of electrons which can be readily donated to another element in the course of a reaction. So both water and ammonia make an excellent neutral nucleophiles. Whether you have a nucleophile that's negatively charged or nucleophile is neutral, there's two types of reactions. One is where a nucleophile is negative, reacts with Rx. Now Rx is your reactant, which I was stating earlier. Every reactant contains two components. One is your substrate and the other is your leaving group, right? Now, if your nucleophile is negative, then the nucleophile is negative, attaches with an R, okay? And it kicks out the leaving group. Because you came with something negative, when something comes out, that must have a negative charge to it, okay? Now, that's not exactly the case when your nucleophile is neutral. The nucleophile is neutral, so it has to donate its electron, which means nucleophile will get a positive charge as it attaches itself to the substrate, which is the R. And as always, when something comes out, it would always obviously have a negative charge. So in both the cases, your X, which is the leaving group, contains a negative charge. But the unique thing is how in one of the products, the nucleophile does not have a positive charge, and in another case, it has a positive charge. It's important that you pay attention to that. Right? Now, just to summarize everything, so these are your nucleophiles. I'm going to move this up. And those are your substrates, and those are your leaving groups. Okay? Now, what is a substrate, and how does that influence the type of substitution reaction or elimination reaction? Okay? Your substrate, remember, is a component of a reactant, right? And depending on the type of substrate you have, you could have a completely different substitution or elimination reaction, okay? Substrate is component of a reactant containing the leaving group, right? It's not the whole reactant is your substrate. It is a component of the reactant containing the leaving group, and I've already told you that is a substrate, right? Now, type of substrates is, you must focus attention to the group containing the leaving group, okay? There could be zillion carbons in your molecule, but how do we determine a particular substrate can go through a particular type of substitution reaction depends on that carbon. It's exclusive, the carbon that contains the leaving group, okay? So in this case, if your carbon that contains the leaving group, which is the Br here, if that carbon contains 3 hydrogens, that's called a metal substrate. Now the carbon containing the leaving group, I've just given different leaving groups just to point out a variety, but it's not the leaving group that's so important here, but it is the carbon containing the leaving group. If it contains 2 hydrogens, then that's a primary. If the carbon containing the leaving group has only 1 hydrogen, that's a secondary substrate. And if the carbon containing the leaving group has 0 hydrogens, that's called a tertiary. It's very important you come back and watch this portion again, because depending on the nature of the substrate, the nature of the the nature of the leaving group does not determine your SN2 or SN1, okay? However, the leaving group has a different effect, which we will see later, but it's the substrate to which the leaving group is attached what controls whether you will have an SN2 substitution reaction or SN1 substitution reaction or E2 elimination reaction or E1 elimination reaction, okay? Let me repeat. It's the substrate that controls what type of substitution or elimination reaction you will have. The leaving group itself does not control the type of reaction that happens. However, the leaving group does control whether a reaction would happen faster or slower, but ultimately it is the substrate that controls whether a reaction would be SN2, SN1, E2, or E1. Okay? Moving on. So we've looked at the nucleophile, we looked at the substrate. So the next logical thing is, you know, we haven't, if you notice, we haven't even looked at what this SN2 means, what this SN1 means. But what I'm doing is I'm setting you up so that when you actually learn SN2 or SN1, it just makes total sense, okay? Everything that you do in it makes much more sense, right? So I've put effect of substrate on the nature of substitution reactions. You have two kinds, SN2 or SN1, okay? Now, if you notice, the arrow is going more towards the metal, wherever the head of the arrow points. And I have actually written down, if your substrate is metal, primary or secondary, it favors SN2, okay? Whereas if your substrate is tertiary based, then it almost exclusively favors SN1. So your metal, primary, and secondary substrates favor SN2 substitution reaction. Your tertiary substrate almost always favors your SN1. Secondary is kind of in between primary and tertiary, but it almost always favors SN2. Your tertiary carbon substrate almost always favors SN1. So there's only one kind of carbon substrate that you really have to know that it favors SN1. The remaining type of substrates almost always favor SN2. Okay? Reaction kinetics. Okay? This is very, very important. I'm not going to have you do any math problems here. But if you remember from your general chemistry, kinetics is nothing but the rate at which a reactant is lost or the rate at which a product is formed. Typically, we write reaction kinetics or rate law with respect to reactants. You could also write it with respect to products, but that's very, very uncommon. You always almost have to write rate laws with respect to your reactants, right? So this is the two, I mean, this, what you just see itself is nothing to do with SN2 or SN1, okay? It just means your nucleophile is negative or your nucleophile is neutral. If your nucleophile is negative, then it attacks the substrate, kicks the leaving group out, and the leaving group comes with a negative charge. If your nucleophile is neutral, then as it attacks the substrate, it leaves a positive charge on the nucleophile and kicks out the leaving group as a negative charge. This is something we looked at earlier. This itself is not SN2 or SN1, okay? So if you have determined, okay, my substrate is primary, so I must most likely have an SN2 type of reaction, then your rate is nothing but rate equals rate constant times. It depends on the concentration of the reactant and the concentration of the nucleophile, which is why it's second order reaction, okay? So if your reaction is SN2, it depends on both the concentration of the reactant. What is this reactant? Well, I've just wrote the rate law for both of the reactions above, okay? So if your reaction is SN2, that means your rate equals rate constant times concentration of the reactant times concentration of your nucleophile. Now, it depends only on the concentration of the nucleophile. It does not depend on the nucleophile itself. So it's negative or neutral. Okay, I've written it for both. The reason is second order is because it depends on both the concentration of the reactant and the nucleophile. Say your reaction is SN1. Say your carbon substrate containing the leaving group is tertiary. That means the reaction would undergo an SN1 substitution reaction. So rate equals rate constant times only the concentration of the reactant. It does not depend on the concentration of the nucleophile. So SN1 reactions are first, SN2 is second. So that's what the 2 stands for in SN2 and the 1 stands for in SN1. 2 indicates it's a substitution nucleophilic reaction that is second order in nature, and SN1 means substitution nucleophilic first order in reaction. So if your substrate is primary, methyl or secondary, that means it's SN2, means it depends both on the concentration of the reactant and the concentration of the nucleophile. Whether your nucleophile is negative or neutral, it does not matter. However, it does depend on the concentration of the nucleophile. SN1, it only depends purely on the concentration of the reactant. Now keep in mind, this is all very generic, okay? Here it's Rx, it's Nu. So when we actually do real reactions, and if I have you write a rate law for it, first you have to determine, you look at the reactant and you determine whether it's got a primary, secondary, tertiary, or methyl carbon substrate, and then you determine whether you write a first order rate law or second order rate law. Based on that, you put one of the reactants in a square bracket if it is first order. If it is second order, then you put both the reactant and the nucleophile in square brackets. This is all generic equation. This is not how you will write for an actual reaction, okay? Now we've looked at the nucleophile, we've looked at the substrate. It's obvious the last thing we want to look at before we actually discuss what SN2 and SN1 is the effect of the leaving group. These are some of the common leaving groups. So imagine your OH, NH2, F, Cl, Bri, and most of you are probably not familiar with what this TOS-O means. It's a tosylate ion. We will come back to it later as we get more into this course. So what I have done here is less efficient leaving group versus high efficient leaving group. So as you go from OH all the way to TOS-O, okay, when each of this is attached to a substrate, okay, if it is TOS-O, that means it has a higher chance to leave quickly when it sees a nucleophile coming in. These have to leave. Okay, so if you have a nucleophile that's coming in and you have two substrate, one contains OH and the other contains say I, the reaction kinetics, which is the reaction that the substrate that contains the I, would be a little faster because the I can come out more readily and the nucleophile can now attach itself, in contrast to your OH, which would be not fast enough to leave the substrate, so the reaction would be a little slower. All right, so this is the level of introduction I want to give to you, and then as we move forward, before I even discuss with you, I do want to take the time to give you some pop quizzes through the video, so you would have to pause the video. And I highly recommend you watch this video at least one more time before you watch the second one. I mean, I know it's not a very long video, so it won't cost you too much time if you have to watch it just one more time. I highly recommend you just watch it one more time because you may miss some nuances in the keywords I have mentioned in the video. I highly recommend you watch this video at least more than once before you go to the second one. What I have done here is I have set you up and made the concept literally simple to the T. So when you go look at the four remaining substitution and elimination reaction, it just seems so effortlessly easy to understand. All right. So I recommend you watch this particular video at least more than once. If you can watch at least once, that would be great. All right. Thank you. Stay tuned for the remaining videos on the substitution and elimination reaction series.